What if I told you that you could multiply two complex numbers just by drawing a straight line between 2 points, no algebra needed? You might wonder, why do it differently when algebra already works? But in maths, exploring ideas from different angles often gives us a deeper understanding and sometimes leads to surprising discoveries. That's why geometry plays such a big role. It's visual, intuitive, and helps us see what's going on. Think about a circle. It has a neat algebraic equation, but let's be honest, without actually seeing the circle, that equation doesn't mean much. It's the shape, the symmetry, the visual structure that brings it to life. And that's the case with many big ideas in maths. Concepts like I or even e to the pi I. They sound abstract at first, but when we look at them geometrically, they start to make sense in a whole new way. So in this video, let's step away from algebra for a moment and explore how multiplying complex numbers can be beautifully simple. For algebra enthusiasts, I is defined as the square root of -1, and it works perfectly within algebraic equations. For instance, the equation x squared equals -9 can be solved easily if you're familiar with the algebra of complex numbers. But it's only relatively recently that we've had a complete understanding of imaginary numbers, and we'll explore them by starting with something we already know well, the real numbers. So here on the screen, we have the real number line. Let's take a quick look at what addition means here. Adding 2 plus 3 gives 5 in terms of movement. That simply means moving 5 units in the positive direction. Multiplication, on the other hand, is essentially scaling. For example, 3 times 2 is 6. It means either scaling 3 by 2 or 2 by 3, we get the same result. But what happens when we multiply by negative numbers? Let's take 2 multiplied by -1. That gives us -2. Geometrically, that's a 180-degree rotation, landing us as -2. Now multiply by -1 again. That means another 180-degree rotation, and we are back to where we started. So what about equation x squared equals -1? We're looking for a number which, when multiplied by itself, gives 1. It can't be a positive number. 2 positives make a positive. It can't be negative either, because 2 negatives also make a positive. So what could it be? How about a 90-degree rotation? Just like multiplying by -1 gives a 180-degree rotation, multiply by I gives a 90-degree rotation. Now let's revisit that equation. X squared equals -1. If x equals I, then x squared equals I squared equals -1. What does that mean geometrically? It means two 90-degree rotations give a full 180-degree rotation. That seems to fit perfectly. So just as multiplying by a negative number gives a 180-degree turn, multiplying by I gives a 90-degree turn. It's simple enough. We reach -1 in 2 steps. Let's say we have a number on a real line. Take 3 for example. Multiply by I and we get 3i. Geometrically, that's just a 90-degree rotation of the number 3. Multiply by I again and we get to -3, which is 3i squared. So rotating 3 twice by 90 degrees gives us a 180-degree rotation, just as we'd expect. Now we are working in 2 dimensions, one real, the plain old real axis, and one imaginary. These axes are perpendicular to each other. Numbers can lie entirely on real axis, like 3, or they could lie entirely on the imaginary axis, like 2i. Or they can be a combination of both, like 2 plus 3i. So once we are on complex plane, everything starts to make more sense. But here's a question. How do we measure the size of a complex number? Take 3 plus 2i for instance. What does its size actually mean? For real numbers, the size is simply the distance from the origin. For example, the size of 4 is 4 units from the origin. The size of -3 is 3 units. And similarly, the size of -4 is 4 units. You get the idea. Similarly, the size of a complex number is also its distance from the origin, and we can calculate it using the Pythagorean theorem that you are already familiar with. Let's see it in action with a complex number a plus bi. Here a and b are the legs of the triangle. Take the example 3 plus 2i. To find the size, we apply the Pythagorean theorem. So the absolute value of 3 plus 2i is root 13, which is approximately 3.6. Addition of complex numbers is quite straightforward. You simply add the real parts to the real parts and the imaginary parts to the imaginary parts. Geometrically, if you represent a complex number as a vector, it's like moving the tail of one vector to the head of the other. The resultant is then the straight line from the origin to the head of the final vector. Multiplying by a scalar is also straightforward. You simply scale both the complex number and its components by the same scalar, stretching or shrinking the number without changing its direction. This affects both the real and imaginary parts in the same way. Similarly, multiplying a complex number by the imaginary unit I rotates it by 90 degrees. Just like we saw with the real numbers, this means the entire complex number, or triangle in this case, is rotated by 90 degrees, changing its orientation but keeping the same size. So every time you multiply a complex number by a real number, it scales the triangle, making it bigger or smaller. Take the number a plus bi for example. Multiply it by a scalar makes it larger in this case. Then when you multiply by I, you are rotating it by 90 degrees. However, when you multiply one complex number by another, both effects, scaling and rotating, occur simultaneously. Let's see all of this in action with an example. We've got two complex numbers, 1 plus 2i and 2 plus 2i, each shown on their own graph. Using the distributive property, we interpret this geometrically. First, we scale the left triangle 2 plus 2i by 1, and the right one we scale it by 2 and then rotate the entire triangle along with its components by 90 degrees. Every part is clearly labeled. Now to add the two graphs. Just like standard vector addition, we shift the right graph and place it at the tip of the left one. Finally, we draw a straight line from the origin to the endpoint. That gives us the result of the multiplication minus 2 plus 6i. For the next few seconds, take a look at the general case and try to justify each step using algebra. As you do, take a moment to really appreciate the elegance of the geometry, how beautifully it all fits together. Now I'd like you to take a look at a few key observations. On the left, we've got two complex numbers, a plus bi at the top left and c plus di just beneath it. We carefully label all the sides so that everything is clear. In the center, you'll see the resultant, which we have obtained using the same geometric method we used earlier for multiplication. Remove the axis plane to keep things clean and focused. Each component is labeled clearly with labels showing the lengths of the respective sides. We mark the angles with different colors. For instance, all the yellow angles are equal and all red angles are equal. This helps us visually identify corresponding parts. The triangles are also colored differently, so we can refer to them without confusion. Now what we are really interested in is the length or absolute value of the resultant. Here, it's the green segment labeled R. To calculate this, we apply the Pythagorean theorem to the central gray triangle But first, we need to confirm it's a right angle triangle. Looking closely at the green triangle, we see that the yellow and red angles add up to 90 degrees. The same holds for the red and yellow angles in the middle triangle, because matching colors mean equal angles. This tells us that the central gray triangle is indeed a right angle triangle. So now we can apply the Pythagorean theorem to find the length of r. When we substitute the values, we find that the result is x dot x prime, where x was the hypotenuse of the top yellow triangle and x prime the hypotenuse of the green triangle. This leads us to a key conclusion. When multiplying two complex numbers, their magnitudes or lengths multiply. Now observe that the gray and yellow triangles are similar. The gray triangle is just a scale version of the yellow one with x prime as the scaling factor. Since they are similar, their angles are congruent too. This means the angle of the resultant is simply the sum of the blue and yellow angles. So we have observed another important fact. When we multiply two complex numbers, we add their angles to find the resultant angle. And that brings us to the end of our journey into the geometric world of complex numbers. As you have seen, geometry doesn't just make things easier to understand, it reveals the hidden beauty of mathematics itself. Algebra tells us how it works, but geometry shows us why it works with elegance, clarity, and sometimes even surprise. Remember what Bertrand Russell once said: the study of mathematics is, if rightly viewed, not only beautiful but sublime. Thanks for watching, and if this sparked a bit of mathematical curiosity in you, then it's been well worth it.